Good morning, everybody. So in the start, I will talk a little bit about MPI3, one-sided communication. The topic is still from our side a little bit premature, I would say, but I hope I can at least give some hints of what has improved and which environment variables and so on can be beneficial for your if you try to use MPI3 one-sided communications. So is that in the past, when you asked developers if they are willing to use one-sided communication, they refused it because they said the implementations were not ready for it and the performance was really bad, so they couldn't use the implementation yet. But I would like to encourage you, after seeing latest results from Cray with this distributed memory app interface and probably some beginning with Intel OmniPath. I'm not sure it's really marked experimental, but at least I was able to run some benchmarks and get some numbers. So that's why I would like to encourage you to give it another try and use MPI3 one-sided communications. Why I will try to motivate, and first what is MPI one-sided communications were already available in MPI2. But I would say that the newest updates in MPI3 made it really applicable. Benchmarks for testing the implementation. So Intel MPI benchmarks has one extra executable that has several flavors of one-sided communications, like unidirectional put and unidirectional get, or unidirectional or put and get with aggregate. And aggregate and non-aggregate means you have iterations, and after each iteration there is a fence called synchronization in the non-aggregate version. And the aggregate version is that you do all your puts or all your gets iterations at once, and at the very end you put the MPI fence call to do the synchronization. Of course, this is delivers much better performance, but probably you can see from the difference what the impact is of frequent synchronization. So for this topic, our final goal, or to use one-sided, I would say, is to overlap communication and computation. So it's really crucial that the progress engine of MPI is continuing when even if calls are not inside even if ranks are not inside MPI calls. There is a famous environment variable to get the asynchronous progress in MPIC, and there are some caveats, so it's not working as intended, but we try to improve that by better maybe I should say this later. So we try to improve this by another environment variable, and I will say something more about this later. There's a project here from ETH Zurich, the one-sided communication in CP2K. I just want to say, show 2 slides of the presentation I got from Alfio, who is present here. And we used to have an MPI working group in the IXPAC community. This is Intel started common community to present newest features or latest features in MPI, and we had a few presentations. Now it's, I would say it's a little bit hibernating because the chair or the guy who's organizing it is now in charge for the total IXPAC, and so we hope that we find some time to revive this working group again. And one of the really interesting talks was given by Alfio about the one-sided communication and CP2K. And last but not least, I would show some Cray-specific options. I'm feeling probably a little bit uncomfortable because I haven't tried them my own, so I just report what I found in a Cray presentation and what might be beneficial to use on a Cray when you deal with one-sided communication. So one-sided communications, typical MPI get usage. This is a little bit sketchy, sorry, but this is strange. No, it's just no, it's just. Can you please help for a moment? It's no, it's coming. Okay, thank you. Sorry.
Just check if we skipped one.
Did I show this one?
No.
No. This would be the MPI2 one-sided communication scheme, typical one that we have in the benchmark. Sorry, it's a little bit very sketchy, but what I want to show is that you first create the memory window here, put inside a buffer with the data and create the window. Then you have to use a fence for the first synchronization before you work with MPI one-sided communication. Then go into the MPI get and get another buffer with size 1 from this memory window that was created on the other side. And then you can probably more overlapping MPI get calls, and finally you use a fence when you go into compute regime again. So what was seen in the past were that we have high synchronization cost because this is a fence call here, and that way is global communication, and so when this whole is not scaling, so of this synchronization cost. And one improvement here for MPI3, I think, is the request-based calls, so that you don't that you can add to an MPI get. It's now called MPI R get because it's request-based, and then you define a request or a vector of an array of requests, and you now can handle the MPI R get or MPI R put in a similar fashion as you did with MPI I send and MPI I receive. But in principle, you need only half of the calls then that you for an I receive I send, I receive pattern, you either use an I-get, R-get, and replace the I receive, and you don't have an send in that case, or vice versa. You replace the MPI I send by an MPI R put with the request handling and no call on the other side. And then you can very fine-grained finish the request by using an MPI wait, as you did for the I send, I receive. So in that case, after that, we would have a compute call to your data, to your computing, and finish everything by an MPI win unlock. And this example doesn't show the whole power of this approach, because normally you would have something like several buffers and try to overlap the communication of several buffers with each other and computation to gain the best overlap of computation and communication. So some benchmarks for testing the implementation. Intel, as I said, has the Intel MPI benchmarks, and a little side information. I shared my office with the designer of the IMB benchmarks for about 10 years, and saw the development. And even right after MPI 2 was designed, he was adding benchmarks for benchmarking the one-sided communication. And there's even an MPI I/O, but this is not interesting now. And there's now an extra executable that is called IMB-RMA for the based benchmarks. Probably one that I haven't shown is most interesting, which tries to measure the overlap of computation and communication. There's some artificial computation in it, and they try to measure how much of the computation is overlapped by the communication. I was trying to play with it, but the results so far were not so promising. I was looking into ITEC. ITEC is similar to Vampire to see the MPI communication. So it's ITEC even supports showing the one-sided calls. And then you can see how much of the communication is really computation is really overlapped by the communication. And some people like more the Ohio State benchmarks, and they offer a similar functionality for MPI put and MPI get. The IMB RMA benchmarks, and you find them to Parallel Studio. I would guess they are here on when you look under opt Intel. You find and MPI, and you find IMB together with the source code. And probably when today I find some time, I can try to compile this with the on your Cray system and try to see how the behavior on your system. And I was using the latest available MPI distribution. You can get a benchmark list here by IMB -RMA-H, and if you are using ordinary or the normal Intel machines, then you can find in the bin directory of Intel MPI the precompiled executable, so you don't have to compile it yourself. I wonder, I guess here on this machine it probably only works in compatibility mode, but we can test. And you find a list of all the available benchmarks. You will see something like 10 different benchmarks, different flavors. In addition to the one-directional puts and gets, you find bidirectional, and you can map this to the original IMB calls like ping pong and ping ping. Ping pong is that a message is sent back and forth between two nodes or two ranks, and ping ping means try to measure the bidirectionality of the network by sending from both sides. So both sides do a send call, and the messages should collide on the network, and it's measuring if you can achieve the double throughput, or if it's just the normal, they share the bandwidth with each other. An important flag that I always would like to motivate is the so-called off-cache flag. So the off-cache flag tries to minimize cache effects. When you use IMB, then roughly the same message is more or less sent 1,000 times back and forth. And a clever compiler will use the cache to improve that. And you see quite severe cache effects in this IMB ping pong, ping ping, and especially for mid-size messages. So for latency, you don't see the cache effects, and in the bandwidth regime, you don't see cache effects as well. But if you go in the mid-range, say 100 kilobyte messages, or 16 to 128 kilobyte messages, then you can see probably very severe cache effects that spoil your measurements. So the measurements of IMB then don't have to do so much with the real measurements in codes. And this flag tries to cure this, and you simply can set it to -1 and then takes a predefined value, or if you see that this is not working, then you can try to put the size here of your cache from your machine as a parameter. And I would try to motivate you, if you use the benchmark, then to think on the off-cache, or try to use both flavors and see the difference, because it can be really severe. So sometimes you see in the mid-range really spikes where you have artificial high bandwidth, which goes away when you switch on the off-cache option. Benchmarks are offered as non-aggregate, which means that there is a win fence after each MPI put or get to finish it. Or in contrast to that, we have aggregate measurements where the win fence is just at the very end. So you continuously write into a buffer, so not the same position, but in a moving position. That is non-overlapping, and then you get, in the end, you will place a win fence to end all the iterations and to finish all the communication. And of course, this is much faster and has much better bandwidth. And you can see what might be the difference from using this in an aggregate way, or putting a fence after each call. For good performance on omnipath networks, I've found using the default OFI fabrics. So OFI, if you have omnipath installed, sorry, because I think you don't have it in-house, even for your small test machine. But if you go somewhere else and work with omnipath, then you find that the new default will be the OFI fabrics if it's installed. And then I was finding in the memory manual that there is a new environment variable for switching on the AMA communication or for improving it. And the plots I want to show from the benchmarks were only possible by switching that on, this one. Before it got stuck in some mid-range, so it was necessary to put this on. But there is some, in the small print of this, it's written that it's still experimental and that it shouldn't work with the, you should use the verbs interface or drivers and not the PSM2 drivers. I don't know, I haven't asked yet for the reason of that. It might be that thread safety plays a role, but I just did PSM2 and for the benchmarks it was working, so just as a preview I used this, and it would be interesting to see how it behaves using that in a real application, and if there are issues with it, probably by with thread safety or other possible issues. So that were my results, and here on the y-axis it's megabyte per second, and here is the number of bytes that is for MPI get, and MPI put. And you see by using the new environment variable, you do about 8 gigabytes here, which is in the range here for these machines, KNL machines, by MPI ping pong with two-sided communication as well. So that's quite promising, because without the flag it would end probably at the half of the bandwidth. So that was quite beneficial, and so we see here the results for the unidirectional get and put. And you see that here the get is still better, but it's just first results. I haven't done too many repetitions, but probably the implementation of get is a little bit easier than the put implementation. Asynchronous communication. So sometimes you see that that communication and computation is not overlapping, and the very reason is that that the MPI is just proceeding when it's on a rank, when it's really inside an MPI call, and otherwise it will just wait. And to get the MPI progress engine, to keep the MPI progress engine running all the time, you have to spawn here an extra thread. And this is done formally with mpitch async progress equals 1. And when you look at it with vtune, you see that you have an extra thread then that's only doing MPI test, I think, and all the time. And Intel has renamed it into IMPI async progress, but I think it's really the same. But as I said here, you have frequent tests here on usage of MPI test to keep the progress engine running. And on KNL, when I tested it, the performance really dropped dramatically. So that was a little bit disappointing that it doesn't work here in the past. It worked on some machines that you get better overlap, but here that was really. I was looking at it with VTune, and I saw the helper thread here that was spawned by using the MPI async progress, and the helper thread was interfering with the ordinary OpenMP threads that I had for the computation. I will show this later. There is an experimental feature to pin the helper threads. So it's already inside the distribution, but it's not documented. But I was trying it still inside. And you can use IMPI progress pin equals and then some numbers nm, and nm is the number of the cores where the progress thread is pinned. So you can pin this progress thread to avoid interference with the ordinary OpenMP threads. So you have to define on which cores the OpenMP threads are running and spare one or two cores, and then pin the helper thread on the empty cores. And you don't see any don't get any feedback when you switch on IMPI debug equals 5, or what's the normal choice. But when you go up to 19 for the experimental features, you get the verbose output and see that it has at least reports to pin the helper thread on the specified cores. So with that, you can cure the situation a little bit, but it's still suboptimal, I would say. And the developer was admitting that there can be problems still with thread safety, that they were using global locks, and there's still a lot of room for improvement for the performance of the helper thread usage. So how does it look like? Sorry, this is a little bit blurry here. And this is the, as I said here, unpinned helper thread. And you have here the OpenMP threads. And you see this special thread is the master thread. And under the master thread, you see another helper thread. And yellow here in VTune is MPI usage. So the helper thread is frequently using MPI. And when you group the VTune, one important feature here is that you can group the display, which means show the display here of the grid in different flavors. And I was using the grouping where I start with core and thread. So I was looking at the cores and saw that one core has had more to do than the others. And then I unfolded it and saw the threads on this core. And I saw that the helper thread was sharing this core with another OpenMP thread. And so this OpenMP thread was running much slower than the other ones and dragging down the whole application speed. So my idea was to keep one or two cores free, like in the core spec of your Cray machine, and put the helper thread on the free thread, free core. Sorry. So that helped a little bit, but it's still not that satisfying. So, few words about an interesting project by Yoko Lazaro. And he was using one-sided implementation in CP2K. and he was using the RMR passive target with MPI arget. So he was using the request-based operations, and probably that was also easier to port because you can directly map then the request-based I send, I receive algorithm that they had before. One output was that they have much less synchronization because it's only half of the synchronization points, I would say. And he says that the overall new implementation is far more flexible. So the performance results were made on a Cray with the DMAP interface, and we have here the three columns, and the first is the point-to-point implementation, step of the one-sided communication, and last not least the one-side implementation with 4 layers. We have probably Alfio will have another presentation someday to explain this. But what we see here is that the weight on the communication is reduced a lot when we go to one-sided communication. So there is the synchronization did not, how I say, decrease too much or even grew up here, but overall the results are quite promising that we achieve here better performance than in the ordinary two-sided communication, point-to-point communication. So next point would be Cray-specific tuning options. And first of all, you can go into the manual if you are on a Cray machine and just do man intro MPI or man MPI, and you can get information for each MPI function here. Tuning through environment variables is possible. Distributed memory application, DMAP AP is crucial for performance of one-sided communication on a Cray, and you enable it by this environment variable, and in addition you have to link to a libdmap library. One specific tuning option that I mentioned yesterday already is that you have this core spec option, that you leave 1 to 2 cores empty for the operation system, and especially for global operations, the interference of the removal of the interference of the OS can bring a tremendous dramatic impact. And they report that when they have collectives with 1 processor per node, which run about 5.5x slower without the core spec option. So in the presentation I saw there was a curve where the with the tickless kernel option the curve was rather flat, while the curve without the tickless with the normal execution was going linearly up the cost. So this should be really tried to use this core spec. It's either, I think, an option in Slurm or in the Cray environment. And you have about factor of 5.5 seen, and for more ranks per node for up to 4.7. So this is really a thing that should be taken into account. So usage of MCD-RAM. So default allocation in MCD-RAM you can get, of course, by what you already experienced yesterday, NUA CTL minus mbind equals 1. Cray has, in that presentation, offered to have more selective MCD-RAM applications through these calls here in MPI alloc mem and MPI win allocate by using info keys. But I was browsing the man pages and I didn't see yet an hint to it. Maybe it's in an upcoming version of Cray MPI. Yeah, and that would be if you want to selectively use the MCD-RAM by using these alloc mem operations. And yesterday you tried already to use the high bandwidth memory interface for allocating and deallocating in MCD-RAM. And that would be even more convenient because then you would have just a parameter to MPI alloc mem and MPI win alloc that you can change in info to change from DRAM to MCD-RAM. So I don't know what's the status here, if they already implemented it or if it's still pending. And one way to find the memory that can be used for MCD-RAM or is a good idea to put into the MCD-RAM would be to use to use vtune. That would be the command line to use vtune for the memory access experiment. And when you do that, you see something like that for the memory access. And first is that it's shown here the memory access for the DRAM, for the MCD-RAM, and you can even split this into read and write. But even more interesting, you can see order what's the most impacting arrays here, and then you can get the allocation, the location of the allocation of these arrays by grouping in that way. And this will, unfortunately, it does not tell you the name of the array, but it does show you where it is allocated, and from that you will, of course, get the right arrays. And you can then go into that routine and selectively allocate only these arrays to MCD-RAM. So that would be a help here. And yeah, now I'm already finished with my part. Do you have further questions to? Yes?
On the previous slide, you had this command line, and was it dash dash or single dash? Sometimes the point turns double dash into, you know.
Yeah, I see the point, but it should be dash dash. But I would say it will even work with single dash.
Okay, cool, thanks.
But dash dash would be more correct. Yeah, probably I try to find some time to do some benchmarks on the Cray system and see how it relates to to the values I measured on our lab machines. Yeah.
So the first graph that you had with this put and get, was this done, or is this done on these machines here?
No.
Oh, okay.
Not yet.
But it is gray KNL, or?
Pardon me?
Is it, these are KNL system?
Yeah.
Okay, but is this gray KNL, or is it with OmniPath?
No, that was with Omnipath.
Okay.
Because that was after the result of setting this environment variable on an Omnipath network.
Yeah, perhaps we could just try the IMB RMA on this system.
Yeah.
And then we would get an equivalent, right? Okay, good. Thanks.
So I have a question. Is it recommended then to develop code using MPI one-sided against MPI two-sided?
Oh, that's a good question. Probably you should maintain two code paths. So if you have a limited communication routine, then I would recommend in the beginning to have your usual code path and probably one switch option where you can go to the one-sided operations. But would be dangerous, I would think, to really design or. So who would be interesting to see more results on the Cray machine? So I would try to generate them today or later. Maybe we can communicate them here through your institution. Okay. Yeah, I would suggest if I just proceed with the next presentation. So, sorry for having not more material on that, but from our side it's quite in the beginning. There are some caveats, so it's not working as intended, but we tried to improve that by better, maybe I should say this later. So we tried to improve this by another environment variable, and I will say something more about this later. There's a project here from ETH Zurich, the one-sided communication in CP2K. I just want to say, show two slides of the presentation I got from Alfio, who is present here, and we used to have an MPI working group in the IXPAC community. This is Intel started common community to present newest features or latest features in MPI, and we had a few presentations. Now it's I would say it's a little bit hibernating because the chair or the guy who's organizing it is now in charge for the total IXPAC, and so we hope that we find some time to revive this working group again. And one of the really interesting talks was given by Alfio about the one-sided communication and CP2K. And last but not least, I would show some Cray-specific options. I'm feeling probably a little bit uncomfortable because I haven't tried them my own, so I just report what I found in a Cray presentation and what might be beneficial to use on a Cray when you deal with one-sided communication. So one-sided communications, typical MPI get usage. This is a little bit sketchy, sorry, but this is strange. No, it's just no, it's just. Can you please help for a moment? No, it's coming. Okay, thank you. Sorry.
Just check if you skipped one.
Did I show this one? No. This would be. Good morning, everybody. So in the start, I will talk a little bit about MPI3, one-sided communication. The topic is still from our side a little bit premature, I would say, but I hope I can at least give some hints of what has improved and which environment variables and so on can be beneficial for your if you try to use MPI3 one-sided communications. So is that in the past, when you asked developers if they are willing to use one-sided communication, they refused it because they said the implementations were not ready for it and the performance was really bad, so they couldn't use the implementation yet. But I would like to encourage you, after seeing latest results from Cray with this distributed memory app, put and get with aggregate. And aggregate and non-aggregate means you have iterations, and after each iteration, there is a fence called synchronization in the non-aggregate version. And the aggregate version is that you do all your puts or all your gets iterations at once, and at the very end you put the MPI fence call to do the synchronization. Of course, this is delivers much better performance, but probably you can see from the difference what the impact is of frequent synchronization. So for this topic to our final goal, or to use one-sided, I would say, is to overlap communication and computation. So it's really crucial that the progress engine of MPI is continuing when even if calls are not inside, even if ranks are not inside MPI calls. There is a famous environment variable to get the asynchronous progress in MPIC and interface, and probably some beginning with Intel OmniPath. I'm not sure it's really marked experimental, but at least I was able to run some benchmarks and get some numbers. So that's why I would like to encourage you to give it another try and use MPI3 one-sided communications. Why I will try to motivate, and first, what is MPI one-sided communications were already available in MPI2. But I would say that the newest updates in MPI3 made it really applicable. benchmarks for testing the implementation. So Intel MPI benchmarks has one extra executable that has several flavors of one-sided communications, like unidirectional put and unidirectional get, or unidirectional